Hello, and welcome to my video where I'll be discussing the Special Relativity public lecture that I went to. So these are the things covered in the lecture. The first thing that was covered is the mysterious way that a slinky falls. Then after that, the rest of the lecture is talking about time dilation when objects are moving at around about the speed of light. A slinky does not drop like any other object when it is exposed to just gravity in free fall. In dropping a fully stretched slinky, the entire thing does not fall at once. There are two stages to a falling slinky, which I'll discuss later. Then, the next thing discussed was the velocity has an effect on our perception of time. So as an example, a train arriving at a station has arrived earlier than the time indicated by the station clock. A person's lifespan can be quote-unquote extended by traveling near the speed of light. When surveying people on how a slinky falls, people thought that it would fall like any normal object. It would just drop to the ground. After filming the fall of the slinky in a fast frame-capturing camera, this was not true. The slinky, when released, stays in midair momentarily. The top of the slinky collapses forward to the bottom of the slinky. Then once the top of the slinky reaches the bottom, once it collapses, the bottom then falls normally towards the ground. However, between the release and the collapse, the slinky is transiently floating in mid-air. This is because when the slinky is released, the bottom of the slinky does not know that there is no longer any upward force. A signal travels from the top of the slinky to the bottom, and as the signal travels down the slinky collapses downward. Once the signal reaches the very bottom, the entire thing falls normally. Until then, the bottom of the slinky thinks there is still an upward force pulling on it until the signal passes by. Therefore, that's why it stays floating mid-air even after released. The next topic discussed was time dilation. As an object moves, its perception of time is slower than that of the surroundings. The object is in one frame, and the surroundings are in another frame. So what happens if an object's speed is closer to the speed of light? Take the case when a person boards a spacecraft, which is then put into orbit around Earth. If the person is moving at 60% the speed of light, for this example, ignore escape velocity, and orbits 6 minutes according to the person, then when he or she returns to Earth, 10 minutes would have passed according to the people on Earth. Here's something to think about. How fast must you travel to live longer? So here are some varying speeds listed in terms of the speed of light. This is a time factor which is calculated by a special formula. According to the person, this much time has passed, and according to the people on Earth, this much time has passed. So for example, if you moved at 90% of the speed of light, then 10 minutes passing by for you is 23 minutes passing by people on Earth. And this value here is calculated by taking this number and dividing it by this factor to get this result. Now as we increase the speed closer and closer to the full speed of light, we see that the time factor gets closer and closer to 0. The time passed according to Earth becomes increasingly large. So for 10 minutes passed at really close to the speed of light, it would be 1.34 years according to people on Earth. The maximum number I could calculate while just being underneath the speed of light is the speed of light minus the machine epsilon precision divided by 2. Machine epsilon is the smallest number that you can subtract from a number for a computer to process. Anything smaller than this, and the computer will round off to 1. So I subtracted this value from C, got this incredibly small time factor. And so if a person was traveling for 1 second at this speed right here, then it would be 1.51 weeks would have passed on Earth. Or to put it in better perspective, 1 year would pass on Earth for every 34.4 seconds a person travels at this speed. And if someone was to travel at exactly the speed of light, then with no time passing, the time passed on Earth would be like the end of the universe and beyond. Incomprehensible. So using this special theory of relativity, can you easily stay young by moving fast? Well, here are some activities done by man, including things like highway driving, walking, running, and fastest spacecraft made by man. And here are some speeds of these activities. So for something like, say, airplane, which is commonly done, which moves at 580 miles per hour, if you're just staying there for 1 hour, then you would be 2 times 10 to the 13th hours younger than everyone else on Earth. And if you were to go on the fastest spacecraft made by man, which goes at 150,000 miles per hour, then if you were to stay in there for 1 hour, you'd only be 3 times 10 to the 8th hours younger than everyone else. So the answer is no. If you were to be even 2.5 hours younger than everyone else, you would have to be in the fastest spacecraft made by man for 100 million hours, or 11,416 years, which is way past your lifespan. This concludes my video lab report. Thanks for watching, and I hope you learned something new. And if you're curious about some certain things, like how I calculate the time factor or what machine epsilon is, you can read it down here.